Hello. In this video, I would like to talk to you about the concept of linear approximation and also discuss the connection of that with differentiability of a function. So remember, we're talking about functions on two variables, but to think about linearization, we are going to remember what you know already about linearization of a function of one variable. So when you learned that, you saw, like in this image, that you had the graph of your function and you were trying to find the equation for a line that would best fit the graph of your function at a very fixed point. So we're going to try to do the same in a setting like this one. So remember that we have our function on two variables. So I'm going to think about my axis x and y to think about the domain, and my z-axis to represent the dependent variable. And I have something like this. And the idea of differentiability will be, okay, I again fix a point, so a comma b, that's my point, and that will correspond to a point in the graph. Say this one right here, that would be the graph of my function. And at this point, I'm going to try to approximate that, not with a line, but because we have now two variables in the domain, this will correspond to a plane. So instead of linearization thinking about a line, linearization for two variables is done with planes. In class, you will see how to figure out how to deduce the formula for this plane that best fits. You will see that there is a strong connection between that and the concept of the partial derivatives. So what I want to show you here is what is the idea of differentiability. So again, think about my point that I decided that is going to be around here in my surface, and I'm trying to approximate that with the plane that best fits. So that's going to be more or less something like this. So yeah, I'm right here, and I have my tangent plane. Great. So once that I have my point there, let's see how that changes. And the reason why I'm doing this is because I'm coming back to the question that I asked you before about if I'm able to detect wrinkles like this. A wrinkle like this is like the equivalent of a kink in a one-dimensional curve, so something like this. Let's see what happens with my tangent plane. So my tangent plane, if I'm in a point like this, look like this, and if I move in this direction, it will continue moving a little bit. The slope, no, not the slope, the inclination of my plane is going to change. So, and then when I get to something like a point in the kink, it's all of a sudden going to change to something like this. And then if I continue going down, my plane is going to vary like this. So what we see that is happening here is that my tangent plane is changing abruptly when I get to this wrinkle, or the equivalent of my kink. And this is totally detected by the idea that, remember, the plane is determined by the partial derivatives. So my partial derivatives are not going to vary too much when I'm moving near this point, but when I get close to here, my derivatives are actually not going to act cool. They change drastically. This is basically the idea that the partial derivatives for a function to be differentiable need to be a continuous function. So that means that when I'm around a point that is in my surface that is going to be a differentiable point in the surface, my partials are going to be continuous functions. And that's a connection. So you have the idea of a differentiable function and the partials to be continuous functions around that point. And now you can see it. This also relates to the idea that the tangent plane is going to be a good fitting or a good approximation for my surface that I have here. If you see with the point that I started, around this point, if I move around here, my plane changes only slightly in inclination, but if I am in a point like this, my approximations go from here to a big jump to here. So here my function is not differentiable because my tangent plane is not also a good approximation there. So you have your equations for the plane, you have the concept of the partial derivatives, and now you're connecting that with the properties of the surface.